Let's dive right into this explainer. Imagine for a second looking at human transportation back in the early 1800s. We're not just looking at it as a cultural norm, but as a monumental, almost impossible physics problem. Back then, we were entirely constrained by the raw biological limitations of literal horsepower. Travel was agonizingly slow, and honestly, wildly inefficient. For engineers and inventors who were just obsessed with finding a better mechanical solution, the ultimate puzzle was figuring out how to overcome those physical limits. The big question was, what if a machine could move on its own? Answering that meant inventing self-propulsion from absolute scratch. We had to completely rethink how human beings moved across the Earth.
So, welcome to this explainer. I am absolutely thrilled to guide you through this today. We're going to take an incredible journey, and we're exploring the evolution of cars, specifically through the eyes of a lead automotive engineer. We'll trace the steps of the brilliant minds who figured out how to get us from point A to point B by tackling massive fundamental hurdles in thermodynamics, aerodynamics, and material sciences. We'll explore the whole shebang from the heavy, clunky constraints of early steam machines right through the roaring internal combustion engines of the Golden Age, all the way to the highly intelligent electric platforms defining our modern era.
Chapter 1. The Engine Revolution.
To really understand this era, you have to put yourself in the shoes of those early engineers. They were facing a massive mechanical hurdle, building a machine powerful enough to replace a horse without it just sinking straight into the dirt. In 1769, Nicolas Joseph Cugnot created a self-propelled road vehicle powered by steam. Now, as a proof of concept, it was groundbreaking, but practically, it was severely limited by its immense weight and incredibly poor power-to-weight ratio. These early mechanical limitations immediately defined the foundational engineering standard for the next century. We desperately needed significantly more power in a much lighter package. Fast forward to 1886 and Carl Benz introduces the Benz patent motor wagon. It only had 3 wheels and a tiny engine, but it solved that weight problem well enough to become widely considered the very first modern car.
The critical breakthrough to bridge that gap was moving away from external steam and into internal combustion. You see, early steam engines were engineering nightmares for personal travel. They were giant, heavy blocks of iron and notoriously difficult to control. The solution? The internal combustion engine. Instead of massive external boilers, we designed advanced pistons capable of withstanding constant, violent internal explosions right inside metal cylinders. But, of course, this created a massive new challenge: thermal management. To keep these engine blocks from literally melting down under the intense heat of combustion, engineers had to develop intricate cooling jackets and radiators. Solving that thermal puzzle, though, meant engines became significantly smaller, far more powerful, and finally ready for the open road.
Chapter 2. Cars for Everyone.
As we hit the early 1900s, the primary engineering challenge shifted. It wasn't just about making a car work mechanically anymore, it was about manufacturing it at scale. Henry Ford completely revolutionized society when he introduced the Model T in 1908, powered by his creation of the moving assembly line. And here's the thing, this wasn't just about speed and affordability. The assembly line forced automotive engineers to completely rethink component design. To build cars faster and cheaper, we had to implement strict, repeatable tolerances and standardized parts. This vast improvement in manufacturing precision didn't just drop the price so millions could buy them, it drastically improved the baseline quality and reliability of the machines themselves. And naturally, this influx of accessible, reliable cars directly caused cities to expand and roads to rapidly improve.
Chapter 3. The Era of Muscle versus Precision.
By the post-war era, global automotive engineering philosophies started diverging wildly. During the 1960s and 70s, the muscle car era absolutely exploded across America, and it was driven by a philosophy of raw, aggressive power. Engineers prioritized massive engine displacement, using super heavy cast iron blocks to achieve mind-boggling raw torque. Speed was king. To deliver that unbelievable horsepower, they practically ignored fuel economy, aerodynamics, and structural rigidity. Honestly, those priorities would be entirely unthinkable to a modern engineer today. But this brute force approach gave us legendary machines that dominated the streets, like the Ford Mustang, the Dodge Charger, and the Chevy Camaro.
Now, while America was chasing that raw power and massive V8 speed, Japan completely changed the game in the 1980s. Their automotive engineers focused on a totally different set of priorities: reliability, efficiency, and technology. As global fuel economy and crash safety regulations started really taking hold, these engineers didn't just focus on engine reliability, they fundamentally altered vehicle geometry. They began engineering calculated crumple zones and dramatically reinforcing structural integrity. Companies like Toyota, Honda, and Nissan proved that precision, efficiency, and deeply engineered safety structures were just as valuable to everyday drivers as pure raw muscle.
And importantly, this focus on efficiency did not mean sacrificing performance. Actually, it birthed a whole new class of affordable performance legends. Vehicles like the Toyota Supra, the Nissan Skyline GTR, and the Honda NSX proved that a highly tuned machine could deliver an absolutely thrilling ride. They achieved this high performance not through sheer brute force, but through advanced thermal management, highly precise electronic fuel injection, and incredibly tight internal engine tolerances. That precision allowed them to rev higher and run smoother than anyone previously thought possible.
Chapter 4: Supercars, Engineering Masterpieces.
As technology advanced further, the internal combustion engine was pushed to its absolute modern limits. Cars evolved from just transportation into high-speed, exotic works of art. To handle engines producing well over 1,000 horsepower, we had to drastically rethink structural weight. We completely ditched heavy steel in favor of ultra-lightweight, incredibly rigid carbon fiber tubs. This shed mass while maintaining and even improving crash safety. But sheer speed creates a whole new problem: lift. To keep these hypercars from literally taking flight, engineers developed incredibly advanced aerodynamics. Think active rear wings and sculpted underbody diffusers. These were specifically designed to create massive negative lift or downforce. These physical advancements allowed hypercars like the Bugatti Veyron and the McLaren P1 to practically rewrite physics in automotive history.
Chapter 5: The Intelligent Electric Future.
Today, we're witnessing what is perhaps the biggest shift since the invention of the gasoline engine itself. For decades, the old perception was that electric cars were strictly slow and, well, boring. Tesla completely flipped a script on that, proving EVs could be fast, smart, and futuristic. For an engineer, this shift is profound. Think about it. Internal combustion requires thousands of moving parts, timing chains, complex cooling systems, intricate exhaust routing. Electric vehicles simplify this mechanically to basically just a battery pack and electric motors. But that simplicity creates massive new engineering hurdles. We now have to manage immense battery weight, engineer flawless cooling systems to prevent catastrophic thermal runaway, and develop highly complex software to manage instantaneous power delivery.
Because of this, modern vehicles are accurately described as computers on wheels. The role of the automotive engineer has fundamentally transformed. A lot of us are now essentially advanced software developers. The mechanical platform, the wheels, the suspension, the chassis, is entirely subservient to a massive overarching digital architecture. We're working heavily with complex code and artificial intelligence. So the vehicle is no longer just a metal box with a motor, it is a deeply intelligent, interconnected computing network.
When you look at the current capabilities of these systems, it is just astounding how far we've come. Modern AI allows some vehicles to parallel park themselves autonomously or pilot down highways without direct human control. And overnight, they can download software updates through the internet to improve braking response or add entirely new features. From an engineering perspective, this artificial intelligence isn't just some luxury add-on, it is being developed as the ultimate structural solution to the single biggest, most unpredictable variable on the road: human error. Looking ahead at the incredible challenges on the horizon, the future of transportation becomes a massive systems engineering problem. We're moving toward fully autonomous cars navigating chaotic environments without steering wheels, the potential of hydrogen-powered engines, and maybe even practical flying vehicles. But the macro challenge is that we are no longer just engineering the individual car. Engineers are now tasked with designing entire transportation networks, perfectly synced and controlled by AI. We're dictating how a vehicle speaks to the traffic lights, the road infrastructure, and every other car in the city, all simultaneously.
And that brings our engineering journey full circle. From the very beginning to whatever comes next, one thing is absolutely certain. Whether it involves managing the intense thermodynamics of a tiny internal explosion or meticulously coding the neural network of a self-driving electric platform, the core mission of the automotive engineer remains exactly the same. It is a relentless pursuit to overcome physical limitations and redefine how humanity moves across the Earth. So I'll leave you with this. What will the next century of transportation look like? Thank you so much for joining me on this explainer. It's been an absolute blast diving into the mechanics of this with you. Keep learning, keep questioning, and I'll see you next time.